Okay. Yeah. Hello, everyone. Welcome to the problem solving sessions for Introduction to Automata, Languages and Computation, Week 6. So, this week we will be looking into what are called homomorphisms or substitution. So, yeah. So, so far we saw regular expressions, we saw what is NFAs, DFAs, epsilon NFAs, and we saw that all these models are equivalent to each other. We also saw some closure properties of regular expressions, regular languages. And this week, we're going to look into another operation under which regular languages are closed. So this is called homomorphisms or substitution. Okay, both are slightly different. So you have substitution. Then so far we saw how to show that a language is regular. So if you want to show that the language is regular, what we did was either we designed a DFA accepting that language, or an NFA or an epsilon NFA or a regular expression. So that was the way we went about showing whether language is regular. But what if the language is not regular? Then how do we show that there is no DFA or there is no NFA and so on? So for that, we use something called pumping lemma, and we will look at several examples for showing that a language is not regular using pumping lemma. And then we will look at an example on Arden's theorem. So this is for showing a language is not regular. And this is closure properties. And Arden's theorem is yet another method for obtaining regular expression from a DFA. So, yeah. So this is going to be the theme of today's the problems in today's week. So let's start with let's quickly recall what are homomorphisms. So a homomorphism is a function from elements in sigma to some delta star. So delta could be some other alphabet. So sigma could be, for example, 0, 1, and delta could be some other alphabet, A, B, C or something. So roughly what it does is it takes one alphabet and replaces it with some other string. So, so as we saw that regular languages are closed under homomorphism. That means if I give you a language and I apply F to it, I get another language F of L, which is over different alphabet delta. And if L is regular, then F of L is, then so is F of L. That is what we know. So, yeah. So we will look at some examples of this kind. So let's see the first example. So let's say you have a regular expression R, which is 0, 0 plus 1 star, 0, 0, 1, followed by 0 plus 1 star. And what does the homomorphism do? Homomorphism basically takes your 0, like we mentioned, it is a function from sigma to delta star. In this case, delta is ABC for us. So what does it do? It takes 0 and maps it to AB, and takes 1 and maps it to BC. Okay, so what we want to do is we want to find what is H of R. So I'll wait for a minute. If you have some idea or your answer, you can unmute or tell me, or you can use the chat box. I'll be looking into it. and then we can discuss after a minute. Okay, so let's see. The given regular expression is the given regular expression is 0 plus 1 star followed by 0 0 1 followed by 0 plus 1 star. Okay, so so what does H do? H basically looks at every occurrence of 0 and simply replaces it with AB, and simply looks at A1 and replaces it with BC. So what would H of R look like? H of R would be 0 is replaced with AB, 1 is replaced with BC, then you have the operation as it is. Then 0 is replaced with AB, 0 is replaced with AB again, 1 is replaced with BC, and 0 and 1 are again replaced with AB and BC. Okay, so this is the this is the string, this is the regular expression for the under homomorphism. Okay, so that is basically part A, which is simply calculating the value under homomorphism. And let's look at B. So here you have a different sort of homomorphism. So okay, so what is inverse homomorphism? What is inverse homomorphism? Let's look at that. Okay, so if you view this as a function, then this basically takes some strings from your alphabet over sigma, and it replaces it with strings over delta, and that's what happens. Like some string here gets replaced with some string here, and so on. Okay, so what is so if this is A, for example, then this is H of A, but there could be different elements here that maybe B, A, and so on, that take you to the same value. So inverse homomorphism basically asks you what all elements map to H of A. So yeah, so H inverse of some X would be set of all Y such that H of Y is equal to X. That's the formal definition. Now let's see the homomorphism function. So H takes A and replaces it with 0 1, takes B and replaces it with 1 0. So let's look at H inverse of 1 0 0 1. Okay, so what does that look like? So notice that if you go to if you ever reach a 1 0 on this side, then it can only come from, then the string has to start with B, because if it starts with A, it would have produced a 0 1, which is not the case. So this clearly tells us that so this clearly tells us that this part has come from B and it couldn't have come from anywhere else. Similarly, you look at the second half, which is 0 1. So there's only one way in which you can get 0 1, that is by taking A. So H inverse of 1 0 0 1 is B. That is the answer for the first part. Then let's look at the second part, which is H inverse of 0 1 0 1 1 0. Okay, so again, so maybe if you would like to take some time and think about it, I'll wait, and you can let me know your answer. Okay, so let's see. Yeah, so again it's the same idea. If you look at 0 1, it can only come from A, so that's what you have. Then again, if you look at the next occurrence of 0 1, it can only come from A, and then you have 1 0, which can only come from B. So that's the answer. Then let's look at the third part. Okay, so this says that H inverse of some language L1 is BA star. Then what happens to H of H inverse of L1? So basically every B is replaced with 1 0 and 1 is replaced with 0 1. So this is what you get. Now the question that is asked is whether it is a subset of the language L, which is 0 0 plus 1 whole star. Okay, so that is L. So the question is this language L prime or a subset of L? Okay, so how do we go about it? Can we obtain 1001 using this? So let's see. First, I mean, from 0 0 or 1 and 1, let's say you choose a 1, then you choose a 0 0, and then again you choose a 1, and then you keep on applying the same sets of operations, and you would get every string in this. So indeed, L prime is a subset of L. So that's a simple exercise on what are homomorphisms, just as a warm up. Now let's look at some properties of homomorphisms. Okay, so we know that languages are closed under homomorphism. So let's look at further properties of how homomorphism can be used. Okay, so yeah. So let's say L1 and L2 are some languages, and we apply this homomorphism. So what you want to show is H of L1 union L2 is equal to H of L1 union H of L2. So do you have any ideas about how do we go about it? Okay, so let's see. What is H of L1 union L2? This is nothing but H of X, where X is either in L1, X is in L1 union L2. And how do we write this? This is H of X such that X is in L1 union H of X such that X is in L2. And if you look at this set on the left hand side, then what is this set? This is nothing but this is the definition of H of L1 union. Similarly, if you look at the set on the right hand side, this is nothing but the definition of H of L2. Because how is H of L defined? You look at every string in L and you simply apply the operation H on every string, and the resultant set that you get is what is H of L. So that is exactly what is written here. So that basically proves the first part. Let's look at the second part. So it says that if you take two languages L1 and L2 and you do a concatenation of these languages and then apply the homomorphism, the result is same as applying the homomorphism on first language and second language separately and then concatenating them. So let's see how to prove this. So we want to show that H of L1 L2 is same as H of L1 concatenated with H of L2. sorry. So yeah, so let's see. Again, let's write what do we mean by h of L1 concatenation with h of L2. This is nothing but h of x, where x is in this language L1 concatenated with L2. And yeah, and how do we write this further? This is nothing but h of x, where x is in L1 concatenated with h of x such that x is in L2. Again, as earlier, we saw that this set is nothing but this set is nothing but h of L1, and similarly this set is nothing but h of L2. So this is also valid. In terms of automata, what this means is if you have if you're doing some sort of shortcutting or expansion on the um, transitions, then it's as good as you do the modification on the first on some part of it, and the modification again on the other part of it, and then simply combine the results. Let's do the C part now. So this says that if you take clean closure of a language L and then apply the homomorphism to it, the result is same as applying homomorphism to it first and then taking a clean closure. So let's see how to prove this. So in C, we want to show that h of L star okay. So let's see how to show this. Again, h of L star, we are just simply writing the definition. So what is this? This is h of L x, where x is in L star. Okay, and this is nothing but h of x such that x is in L concatenated with this thing to the star. And this slight abuse of notation, what I mean by this is you look at every string here and apply the star operation on that. So yeah, so this is nothing but h of L star. Are there any questions about this? If not, then I'll move on to the next question. So okay, so homomorphisms can be thought of as a tool to prove that a language is not regular. And how is that? So what we said just now is that if L1 is regular, or let's say if L is regular, then any homomorphism f which has to be regular. If you just look at the contraposition of this, then what it means is if h of L is not regular, then L is not regular. So what does that mean? If I want to show that L is not a regular language, what I'll do is I'll come up with a homomorphism H and show that and come up with get an H of L, and H of L is some known non-regular language. Using this fact, I can conclude that L is also not regular. Okay, does that make sense? Okay, so if that is clear, can you like maybe take a few minutes and see whether the language L1, which is defined as 0 to the n, 1 to the 2n, 2 to the 3n. So here the alphabet is 0, 1, 2. So can you show that L1 is not regular using this part? I mean, using this idea of homomorphisms. Okay, so okay, let's discuss. So the first non-regular language that you probably might have come across is a simple language, which is 0 to the n, 1 to the n for n greater than equal to 0. So we know that this is not regular. This is something we showed using pumping lemma in class. Now, the language that is given to me is 0 to the n, 1 to the 2n, 2 to the 3n, where n is at least 0. So what I'm going to do is I'm going to come up with a homomorphism and somehow get to this language or something similar to that. So what I'll do is I'll take 0 and under h, 0 gets mapped to a, and I'll take 1 and, or maybe let's not use a different set of alphabet. Let's say okay, let's take the same alphabet. Let's say h of 0 is 0, h of 1 is also 0, and h of 2 is 1. So what happens to L1? H of L1 is basically 0 to the n, 0 to the 2n concatenated with 1 to the 3n. Why is that? Because we simply looked at 0 in L1, replaced it with 0, 1 in L1, replaced it with 0, and 2 in L1, which was replaced with 1. So this is nothing but 0 to the 3n, 1 to the 3n, where n is greater than equal to 0. Now, using similar arguments that we saw in pumping lemma, so here this is directly not exactly L, but using similar arguments as in pumping lemma, it can be shown that this language is also not regular. So yeah, so what that means is h of L1, h of L1 is not regular, and hence we know that L1 is not regular. Okay, so I'll maybe let you stare at it for a while, and if there are any questions, do let me know. Okay, so if that is clear, let's try to do the second example. So L2 is basically a b to the n, cd to the n plus 1, where n is greater than equal to 0. Okay, so what is the obvious it already sort of gives you I mean, a familiar structure as the language that we saw, 0 to the n, 1 to the n. So the idea is that we somehow want to take this first part of it, first n plus 1 length part of it, and map it to zeros or some, and take the second half part of it and map it to ones. So so what is the obvious homomorphism? You take A, map it to 0, look at B, map it to 0, and look at C, map it to 1, look at D, and map it to 1. So what does H of L2 look like? It looks like 0 because A is replaced with 0, or let's take one more step. H of A, H of B to the n, followed by H of C concatenated with H of D, whole thing to the n plus 1 for n greater than equal to 0. So now we're just going to look at each of this h of a, each of these values from the function that we just defined, and we're going to replace it. So h of a will be replaced with 0, h of b with 0 again. Then h of c is replaced with 1, h of d with 1, and okay. So this is nothing but 0 to the n plus 1, 1 to the n plus 1. Okay, sorry, I think I slightly need to modify this, because if I just replace h of d with 1, then I get 1 uh, 1 to the n plus 1, which is nothing but 1 to the n plus 1 concatenated with 1 to the n plus 1, which is nothing but 1 to the 2 times n plus 1. And this is not what I want for the moment, because the language that I am referring to is n ones followed by n zeros or something. So what is so I mean, you can still work with that and still show that language is not regular. There's not much difference in the argument. But if I want to directly get to the language, what I'll do is I will simply replace d with epsilon. So what happens now? This becomes epsilon, and what I get here is exactly what I wanted. I get n plus 1 zeros followed by n plus 1 ones, n greater than equal to 0. And this language is something that we have already shown is not regular. So h of L2 is not regular, and therefore this implies that L2 is not regular. Okay, so yeah, so this is how you basically use homomorphisms. Of course, you can use pumping lemma to show that something is not regular, but this is, if you can already reduce to some other known language which is not regular, then it sort of saves you a lot of effort. So that's how you can use homomorphisms to show that languages are not regular. So here is an obvious question that one can ask. So we said that if L is regular, then H of L is also regular. But is the other way around true? Is it true that if H of L is regular, then L is regular? So I'll pause I'll let you think for a minute. Okay, so let's discuss the answer. So the answer is no. Um, so for example, again we'll take our favorite non-regular language, which is 0 to the n, 1 to the n, and greater than equal to 0. And I will come up with a homomorphism as follows. So h of 0, let's say, maps it to A, and h of 1 maps it to epsilon. Okay, so what does h of L look like? H of L simply replaces, yeah. So let's write down this formally, because there are a lot of steps that we can skip, but okay, just so that we use the properties that we saw in question 2, let's write it step by step. This is nothing but h of 0 to the n, 1 to the n for n greater than equal to 0. This is nothing but h of 0 to the n concatenated with h of 1 to the n for n greater than equal to 0. And this is nothing but h of 0 written n times concatenated with h of 1 written n times for n greater than equal to 0. So the first step follows from the distribution under distributive property of homomorphism under concatenation, and second one follows from the clean star sort of thing that we saw, the property. Okay, so now we will simply write 0 as A, um, A to the n, and h of 1 is simply epsilon, so epsilon to the n is also epsilon. So this is nothing but A to the n for n greater than equal to 0, which is nothing but A star. Okay, so we know that h of L is regular. So here is a language, this is regular. So here is an example of a language L where L is not regular, but h of L is regular. So yeah. So yeah, it is not necessarily true that if a language is regular, then h of L has to be, if a language is not regular, then h of L must be non-regular. Are there any questions about this? Okay, so yeah, so now we will do some examples on pumping lemma. So just to recall, what is pumping lemma? So pumping lemma is a property of regular languages, which says that if L is a regular language, okay, then there is some string x, okay, which can be written as u concatenated with w. Okay, okay, so just to be clear, x is not just any regular language, but x is a regular language that accepts a string x whose length is more than let's say the number of states. Then there is some splitting of x which can be written as u v w, where length of uv is p, or let's say is n, and you can and v is not epsilon, then every u v to the I w for I greater than equal to 0, this string would end up in the language. Okay, so so intuitively what we are saying is, if you start with this state and there is some automaton defined here. This is, let's say, one of the final states that you have. Then if there are n states here, then without repeating any states, how many what can be the maximum length of a string that reaches final state without repeating a state? So for example, if it starts at 1, goes to 2, then maybe like goes to 4, then you and so on, then you are never allowed to come back to the states that you have already visited. So since there are only n states, your string can only have at most n length if you are not allowing, or n minus 1 length if you don't allow repetition. So if it does repeat a state, then it must happen that it sort of visits some state here, and there is a loop between there is a loop. So if the loop is there, then you could basically you could have gone across that loop as many times as you want, and hence you would so this basically captures that thing. So v to the I sort of the expression corresponding to the loop, and what it says is, oh, if you would have ever repeated a state, then you could have repeated it as many times as you want. So that is basically the statement of pumping lemma. So if you want to show that a language is not regular, then you would want to show that this property is violated for some x. So that is what. So in particular, you cannot obtain this sort of, you can't have any breaking of x into UVW satisfying these conditions, such that, okay, sorry, this is when I'm talking about length, I shouldn't talk about epsilon. Okay, so this is what I meant, greater than equal to 1. So yeah, yeah, if you go on pumping, then you get a string in the language L. So if you want to show it is not regular, you will have to show that one of the properties is violated. So let's see with an example. So okay, sorry, so this should have been, okay, it doesn't matter. So if I want to show that L is a set of all W such that W is not a palindrome, I want to show that this language is not regular, then it's as good as showing that L complement, which is nothing but set of all W such that W is a palindrome. It's sufficient to show that L complement is not regular. Okay, why is that? Because we know that regular languages are closed under complementation. So if L bar were regular, then so would L be, and hence if it's sufficient to simply show that L bar is not regular. So let's see how to do that. So this N that we talked about here, this is called a pumping length. It's just a term used, pumping length. Okay. Okay, so yeah, so let's look at how to show that L complement is a this language L complement is a non-regular language. So what does L complement look like? Assuming that sigma is 0, 1, L complement would have strings like 0, 1. So palindromes are basically those strings that if you read from left or right, it reads the same. So for example, ABBA is a string that if you read from left, you get the same thing. If you read from right, you get the same thing. In particular, W is same as W reversal. If that happens, then you say that the language is a palindrome. The word is a palindrome. So what does L look like? It looks like this. Then you can have 0, 1, 0. You can have 1, 0, 1. You can have 0, 0, 0, 1, 1, 1, and so on. There are infinitely many strings in the language. So in order to show that it is not regular, what I'll do is I'll in particular take the string 0 to the n, 1, 0 to the n. Is this string a palindrome? Yes, because if you read it from left to right, it still reads 0 to the n, 1, 0 to the n. So this, okay, so this is the string. And what is the pumping length? The pumping length is n. So that means uv is nothing but 0 to the n. Now, u may be some L length string and V may be some n minus L length string and V may be some L length string where L is strictly greater than 1, because remember that is the second condition that we had here. So first condition here was that UV has to be of length n and V has to be at least of length 1. So that is what we have. Okay, now let's do the pumping. So what does uv to the I? W. Okay, so in this case w is nothing but 0 to the n. What does this look like for, let's say, I equals to, this would be 0 to the n minus L followed by v to the 2L followed by 0 to the n, which is nothing but 0 to the n plus L concatenated with, sorry, this is 1, yeah, concatenated with 1, 0 to the n. So if you look at the number of zeros in the on the left hand side, then there are n plus L, which is strictly greater than n many zeros. And if you look to the right of 1, then there are only n many zeros. So this is not matching, because if you take a reversal of this, then it would be 0 to the n, 1, 0 to the n plus 1. This is not the same as 0 to the n plus L is not the same as 0 to the n. So this is not a palindrome. So by pumping this, we are able to get a string which is not in the language. So this is clearly against the properties of regular languages, because that's what the third condition is. Third condition says that if you pump it this way, then you will always end up getting a language, getting a word in the language. So in this case, this is not in L, not in L bar. So L bar is not regular. And this implies that L is not regular. Okay, so I'll let you stare at this for a while, and you can also attempt the second question, which is the set of all strings of the form W, T, W. Okay, we want to show that this language is not regular using pumping lemma. Okay, so let's look at the part B. So part B says that if L is set of all W, T, W such that W in 0, 1 or W comma T in 0, 1 star. Okay, then yeah, you want to show that this is also not regular. So how do we show this? Again, you can basically follow the same steps as we saw in the previous example. Notice that this is a this is nothing but the set of okay, this is not exactly palindrome, but okay, but the same example would work, because let's say you take W to be 0 to the n and T to be 1, then then your x is 0 to the n, 1 followed by 0 to the n, because that is what the string that we have been given is. So, so here again the pumping length is n. So this can be written as UVW. So same as UVW, where U is 0 to the n minus L, V is 0 to the L, where L is greater than 0, and W is 1 0 to the n. So again, if we apply the pumping thing, what you get is U V square W should be in language L. So let's see whether that happens. So U V square W is nothing but 0 to the n minus L followed by 0 to L followed by 1 0 to the n 0 to the n, and this is nothing but 0 to the n plus L 1 0 to the n. And again using the same argument, you can see that the string on the left of t and the string to the right of t are clearly different. So this is not really of the form WTW, and hence this is not in it. Okay, so it's basically the same idea, even though this strings that we have written here is not a palindrome. L is not a set of palindromes, it's something different, because in palindromes you have W followed by W reversal, whereas L could have strings of the form 0 0 1 0 0 1. So this is a valid string for L that we are talking about in B, but this is not a palindrome. So notice that the examples are different, but the same string for pumping lemma that worked for the previous example also works for this example. Okay, then next let's look at this. This is a slightly trickier one. So let's look at this. So C is the set of all strings of the form 0 to the I, 1 to the j, such that I is greater than j. Notice that we know that the strings of the form 0 to the n, 1 to the n for n greater than equal to 0, this is not regular. But that does not directly imply that this is not regular. So maybe you can think about this for a minute and then we can discuss this. Okay, so this one is slightly different from the previous examples, where it was more like, okay, let's look at this. So maybe look at 0 to the n plus 1 followed by 1 to the n. So this language is in this string is in n because the number of zeros is clearly more than the number of ones. Okay, but yeah, but let's try to break this string now in the form of UVW. So length of UV is n. So UV is nothing but 0 to the n. So if we try to break U and V, you get U is some 0 to the n minus L and V is some 0 to the L for L greater than 1. Okay, and W is nothing but 0 followed by 1 to the n. So what happens now is, if you try to do pumping, you get U V square W. This happens to be 0 to the n plus 1 plus L followed by 1 to the n. So since L is greater than 0, the number of zeros is clearly more than number of ones, and so this language would end up in L. So no matter how you split the zeros between U and V, you will never arrive at a contradiction. So if you directly sort of try to pump the strings, you will not end up getting something outside L. So yeah, so we will see how to get around this, but before that I want to talk about, so this is the sort of difficulty if you apply, if we try to pump the strings. Okay, but let's see, before we actually use the pumping lemma, let me show a way of showing that this is not regular. So let's say that L prime were a language where okay, so L is this yeah, let's say L is this language where you have set of 0 to the I, 1 to the j, such that I is greater than equal to j, let's say L1. Then L2 would be, if you simply apply homomorphism, then you can replace zeros with okay, maybe there is no direct way, or at least I can't recall it now. So maybe I'll try to do the pumping lemma first. Okay, so one thing to notice is that whenever we apply the pumping lemma, it says that u v to the I w should be in the language for all I greater than equal to 0. That means in particular the string u v to the 0 w, which is equal to uw, should be in the language. So let's try to use this. Suppose x that we are looking at is 0 to the n plus 1 followed by 1 to the n. Okay, now let's try to break this. So again, u is some 0 to the n minus l, v is some 0 to the l, and w is 0 followed by 1 to the n. Now what is u concatenated with w? It is nothing but 0 to the n minus l concatenated with 0, 1 to the n, which is nothing but 0 to the n plus 1 minus l, 1 to the n, where n plus 1 minus l is strictly less than equal to n, because L is strictly greater than equal to 1. So here you don't get a string which has more number of zeros followed by less number of ones. Here you get strings which are at most of length, which have at most as many zeros as ones. So this is not an L, and that is enough for us to say that using pumping lemma, this string is not in the language, and therefore the language is not regular. So this notion of using the fact that I is equal to 0, this is called pumping down. So sometimes when pumping up is not useful, it's sometimes useful to pump down, which is by using a shortcutting the W and simply looking at UW. Okay. So if there are no questions, I'll move on to the next one. Okay, this is slightly tricky. Okay, so you have been given two languages, B and C, which are as follows. So B is a set of strings of the following form. You have k many ones followed by a string y, where y has at least k many ones. So B somewhat looks like you have, let's say 1 1, then you can have a string like 0 0 0 1 1, where B this is a block of ones, and the following block has at least 2 ones. Then you can have 1 followed by 0 1, where you have a block of 1 1 followed by y which has at least 1 many ones, and so on. And C is exactly opposite. C has a block of k ones, and then you have a y which has at most k many ones. So you want to tell which of the following, like which of B and C are regular. Is it that only B is regular, or is it that both are not regular, or is it that C is regular, or that both are okay, sorry. So this option D is um, yeah. So option D is that both B and C are regular. So this is some typo. Okay, so please read it at this as this, and now I'll maybe you can take 1 minute to think about it, and if you have some answers, please type in the chat. That will help the discussion, and we can discuss. Okay, so okay, so if there are no guesses, let's see. Let's see the solution. So the answer is that only B is regular. So correct answer is A, and let's see why. So if you want to show that something is regular, what do? You basically show a regular expression or a finite automaton for the same. So in this case, B is nothing but a bunch of ones followed by a string y, where y contains at least k ones. Okay, so this is nothing but uh, you can think of this as there is a 1, and after that there is a string y prime, where y prime is equal to bunch of okay yeah, where y prime is nothing but a string consisting of at least one occurrence of 1. Okay, so this is what the string is. This is what the language is. So, what is the regular expression for this language? It is nothing but 1 followed by, or if you want to think about the automaton directly, it's basically that you start at this state, then you read a 1, and then after that you want to read at least 1. So maybe you read a bunch of zeros, ultimately you read a 1, then you go to the final state and you stay there because you've seen at least 1. So that is basically the automaton corresponding to the language B. So since you can design a DFA, the language must be regular. So therefore, B is regular. Okay, now C. Let's look at the language C. So C looks very similar to B, just that there is a flip in the inequality. But why is it that B is regular while C is not? So let's see. C is set of all 1 to the k y such that y has at most k many ones. Okay. So how do we show that a language is not regular? So far we have seen that either you can show that using homomorphisms that h of L is not regular, or you can use pumping lemma. So let's try to use pumping lemma for this. So Yeah, so let's look at this language 1 to the k, 0 followed by 1 to the k. So this string is in C simply because y has at most k many ones. Okay, so this is in C. So let's say this is x. Now we want to break x into the following u, v, w such that length of uv, all of this is coming from pumping lemma. So length of uv um, is equal to k, and length of v has to be at least 1. So what does that mean? That means u is some bunch of ones and v is some bunch of ones such that L is greater than 1 and W is the remaining part of the string. So this is how you can break X. Okay, now let's do pumping. But like we saw in the previous example where you wanted to the number of zeros before the preceding number of zeros have to be more than the following number of ones. What we did was, if we try to do the normal sort of pumping up thing by doing u v square w, then this was not working. But what we did instead was we used this trick of pumping down. So we used the fact that I is equal to 0. So let's try to do the same thing. Okay, because here also if you pump up, the number of ones only goes up, and that is not working in our favor. So let's do u v to the 0 w for I equals 0. So what is this? What is this string? This would be 1 to the k minus L followed by 0 to the 1 followed by 0 1 to the k. And since L is strictly greater than 1, the number of ones here is strictly less than k. Okay, so that is clearly not the language that we wanted. The language here is that you have bunch of ones, and the following y has at most that many ones. But here the following y has more ones than what you had previously in the block of ones. So this string is not in the language. Okay, so therefore by pumping lemma, C is not regular. So again, the trick that we used here was that we sort of pumped down to obtain this uv to the 0 w. So sometimes when pumping up is not working, you can always try pumping down. So that's like a useful trick to keep handy. Okay. So if there are no questions, are there any questions about this? Or is there some part that you want me to repeat? To let me know. Okay, so if not, I'll move on to the next question. Okay, so here you are given a DFA and you want to find a regular expression for it. So in the previous week, we saw how to convert a regular expression, how to obtain a regular expression from a DFA. So we had drawn this table and it was sort of formula way of getting regular expression. And Arden's way is another method. So let me quickly okay, maybe you can try this for a minute, and if you have answers, you can write in the chat. Otherwise, we can discuss. We can discuss in a minute. Okay, so let's see. What is Arden's theorem? Arden's theorem basically says that if you have two regular expressions, R and S, then if you have equation of this form, x is equal to s plus xr, and r does not contain the empty string epsilon, then this equation has a unique solution. And what is the solution? The solution is x is equal to s r star. So I'm not going into the proof of this because this was already done in the lectures, but what we will do is we will assume this theorem to solve to obtain a regular expression. So how to do that? We will obtain expressions for each of the states. So what is the regular expression for the state A? Let's say A denotes, this is again misuse of notation, A is already denoting state, but A here denotes the regex for state A. Okay, so how do we get at A? You can reach A by simply not reading anything, or you can reach A by reading 0 and coming back to A because you have a self loop here on 0, or there is another way of getting to A, which is via B. So if you are at B and you see a 1, then you can go to, sorry, this is A followed by 0 and this is B followed by 1. Similarly, what is the expression for B? The expression is you can get to B from A by reading this 1. So here you have A followed by 1, and and if you are at B, there is a self loop on B which is on 0. So if you are already at B and you see a 0, then you reach at B. So these are the two equations that we have. Okay, so now if you think about this as in the form of this equation, x is equal to s plus xr, then what do we get? So here b is nothing but x, this is nothing but s, b is again x, and 0 is r. Okay, now we apply the Arden's theorem because R does not contain epsilon. R is just 0 and it does not contain 1. So we can apply the Arden's theorem directly. So what does that give? It says x is equal to s r to the sr star. So s is nothing but a1 and r star is 0. So which is 0 star. Okay. So now let's now that we know that b is nothing but a10 star, what we will do is we will plug and place this value in the first equation. So what does that give? It gives a is equal to epsilon plus a0 plus b will be substituted with a10 followed by 1. Okay, now this can be written as epsilon plus a 0 plus 1 0 star 1. Okay, so we basically found this common factor a and wrote everything else in the brackets. That is the simple thing that we did. So now again this expression a is in terms of a only, so we can use Arden's theorem. So let us identify what is x, r and s again. So a is nothing but x, epsilon is r s, a is again x, and this remaining expression is r. Now notice that the condition only says that R should not contain epsilon. It is okay if S is epsilon or S contains epsilon. There is no constraint like that. So here in this case, S is epsilon, which is completely okay. The only thing is R should not contain epsilon, which it doesn't. So we can again apply Arden's theorem. So what it gives is, it gives you x is equal to S R star, which is nothing but A is equal to which is nothing but A is equal to S is epsilon, R is 0 1 0 plus 1 0 star 1 star. Okay, and Yeah, and now if we plug and place this value of a in b here, what we get is b is nothing but 0 1 0 star 1 star followed by 1 0 star. Okay. Okay. So yeah. So if there are no questions, let's move on to the next question. So I think this is the final session. This is the final question that we have for today's session, and yeah. Okay. So again, you're going to use pumping lemma to show that the following languages are not regular. So let's see how to do that. Okay, so let's look at the first language. L is the set of all 0 to the n such that n is a power of 2. Okay, so what does L look like? This is 0. Then you can have 2 zeros. Then you can have 4 zeros. Then you can have 8 zeros, and so on. You can have 16, 32, and so on. Okay, so this is the language L. Okay, so let's see how to prove this is not regular using pumping lemma. So let's look at this string 0 2 to the k. Okay, and let's say that k is large enough so that 2 to the k is greater than the pumping length p. And notice that this is always guaranteed because this set L is infinite. So for if P is somewhere here, then you can always find a string beyond this because there are infinitely many strings. Okay, so let's say this is our x. Now again, like earlier, we are going to break x into 3 parts u, v, w, such that length of uv is equal to p and length of v is greater than equal to 1. So how do we do that? So u will be some string 0 to the 2 to the uv will be some string 0 to the 2 to the k minus okay, sorry, this is of length p, so this will be 0 to the p followed by 1 to the followed by 0 to the 2 to the k minus p. Okay, now we will further break down uv into smaller pieces so that v has length at least 1. So let's say u is actually of length p minus l, v is of length l, and l is greater than equal to 1, and w is the same, 0 to the 2 to the k minus p. Okay, so now let's try to pump again. So what do you get? You get, if you do u v square w, then you get 0 to the p minus l followed by 0 to the l square followed by 0 to the 2 to the k minus p. Let's add this. What do you get? This is 0 to the p minus l plus 2l plus 2 to the k minus p. So this p and this p cancels out. What you get is 0 to the 2 to the k plus l, where l is greater than equal to 1. So what should be the value of L so that 0 to the 2 to the k plus L is a power of 2? If it has to be some power of 2, then L will have to be at least 2 to the k. Otherwise you can't get a power of 2 because 2 to the k plus 2 to the k, that would be 2 to the k plus 1. But if this value here is not sufficiently large, then you can never reach to 2 to the k plus 1, which is the only power of 2. So after 2 to the k. So if you have 2 to the k here, everything else here is not a power of 2. The next power of 2 is only 2 to the k plus 1. But if you don't have sufficiently many L's, then you will never ever reach to 2 to the k plus 1. So you will be stuck somewhere here. And um, And L is nothing but, if this is your P, then L is some part of this, some non-zero part of this. But by choice of P, by choice of K, notice that where did I write this? Here. So by choice of K, you have that P is at most 2 to the K. So, or maybe you can basically choose a P which is slightly larger. So what you have is L is at most, L is strictly less than P, and P is strictly less than or at most 2 to the K. So if L is really is smaller than 2 to the K, then you can never ever reach to 2 to the K plus 1. So you will never, so this string is not a power of 2. And therefore, this string will not be in the language L. So, that is basically the proof of pumping lemma. What we did is we chose a k large enough so that it 2 to the k is more than p. Then we simply broke down next into different parts basically. And when you do this u v square w, you end up getting a string of length 2 to the k plus l. But L is not large enough to get a power of 2, so you simply get a contradiction that there is a string of length which is not a power of 2 and it is still in the language. So this is a contradiction. Therefore, the language is not regular. Now, let's look at the final question. So part B says that L is a language of the form a to the n, b to the l, c to the k, where n plus l is equal to k. Okay, so what does this look like? This is nothing but strings of the form maybe A, B, C, C. Then you have maybe A, B, C, 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 and so on. That's strings like this. So, yeah. Yeah, so let's see how to show that this language is not regular. Again, the idea is very similar to what we have been doing so far. Let's say that P is your pumping length. So here is some string P plus L. So because the number of C's here is equal to the sum of number of A's and number of B's, this string is clearly in the language L. Okay, so where is UV? So this string here is W. So and UV is here. So UV is nothing but A to the P, and W is nothing but C to the P plus L. B to the L followed by C to the P plus L. Now we are going to break UV further so that V has some non-zero many ones. So U is going to be some A to the P minus L many A's, and V is going to be some L many A's where L is greater than equal to 1 and W is the same. This is B to the L, C to the P plus L. Okay, so now let's simply apply pumping lemma. What does it say? U V square W should not be in the language. So let's see what happens. So you get U is A to the P minus L, V is A to the L whole square, and then you have B to the L followed by C to the P plus L. This is nothing but A to the P plus L, B to the L, C to the P plus L. But now let's look at the sum of number of A's and number of B's. So number of A's plus number of B's is nothing but P plus L, which is more than p plus l and not equal to p plus l, which is nothing but the number of c's. So here you get a string where number of a's plus number of b's is not equal to the number of c's. So this string should not be in the language, because that's what the definition is. So you have a string in language if and only if the number of a's plus number of b's is equal to the number of c's. So yeah, so you get that u v square w is not in L, therefore L is not regular. Okay, so yeah, so that is how you show using pumping lemma that a language is not regular. And I think, yeah, that ends the set of questions that we had to discuss for today. So we looked into a few examples of homomorphisms, their properties, and we saw how to obtain regular expression from DFA using Arden's theorem. Yeah, so next week we will be looking into some examples of minimization of DFA. That is, if I give you any DFA, how do you get a DFA with smallest number of states, as small number of states as possible. So yeah, and yeah, we'll discuss things like this. Yeah, I think if there are any doubts, I will stay in the call for 5 minutes. Yeah, but I'll stop the recording for now.